Well, greetings, mathletes, and welcome back. We're continuing to talk about exponential functions today, but we are going to introduce a special guest, which is the number e. Um, Now, the number e is one of those things that it seems to pop up everywhere, especially in sciences. Um, but this function, um, well, let me just write it this way, make sure. Oh, come on. There we go. Okay. Um, let's start with the number e. First of all, the way it's found, um, it's an irrational number, so you can't write the whole thing down as in standard form. But it's an irrational number like pi, which is why we use a symbol for it. The way you find it is you take this quantity 1 plus 1 over n to the nth power. Now, it seems like kind of a funny little expression there, but if I let n get bigger and bigger and continue to get bigger off into infinity, what I end up with is the number e. So the bigger n gets, the closer the number gets to e, is basically the idea. But this number right here, um, it shows up in atmospheric density models. It shows up in population models. It shows up in what's the other one? Let's see, compound interest. It shows up in compound interest. Um, God, it shows up in so many places. This thing is really, really super common. It actually gets used in psychology a lot when you're talking about things like the learning curve. Um, so yeah, the thing is everywhere, and it's almost magical how much it shows up. So we're going to be using this as our base today, is what we're going to be doing. So we're going to be talking about a few different things, but they are going to be in the context of this number e. Um, so let's go ahead and start just by getting used to the number, getting used to using it on our calculator, getting used to computing powers of e, because the functions that we're going to be looking at are all going to more or less be in this form, where you have some number times e to some constant to the t power, right? So a and k are just numbers. E is the number, right? And t is your variable in this case. Now, um, if you want an estimate of e, so you do find it on your calculator. You see this button that says ln. There's usually on all scientific calculators some button that says ln, and it's usually a second function to the ln. It's e to the x. So, where's this the second function? Right. So now we have e to the some power, and if we want e itself, we'll type in 1, right? E to the first power. And e to the first power is that. That is not an exact number, that is an estimate, that is rounded off. But e is approximately 2.71828 da 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 da, right? It's going to keep on going forever. Right? This calculator just takes it out as far as it can. Okay, so to start off with, what I'd like to do is just make sure we can use our calculators to take powers of e. So first off, and I'm going to just have you try these, so you will need your calculator. If you need to pause this and run and grab it, go ahead and do so. The first thing I'd like you to do is just make sure you can compute e to the first power, right? Just make sure you get this number. And that's what we'll be doing to start out with, making sure that you can type these things into the calculator so that you can get an appropriate decimal approximation of these. Okay, so here's what I want you to try to compute. So first of all, let's try to do e to the fifth, and then e to the 1/2 power, e to the -2 power, and then e to the square root of 3. Right? So these are all quantities. These are all types of things that we may have to compute. So go ahead and pause it here. Make sure you can get those things to fall out of your calculator, and then we'll compute them. And you'll be able to see on the screen here how to plug things into the calculator. Okay, I'm assuming you've paused. So let's start with e to the fifth. So we got second function. So we got e to the fifth power. It's always a good idea to close those parentheses, although I think the calculator actually anticipates that you meant to close it and gives you an answer anyways. Okay, so we got e to the fifth is approximately 148 point. Let's just do 3 decimal places on these. So we'll do 413. Okay, now e to the 1/2. Now remember, a 1/2 power, what that actually is computing is a square root. We're actually looking at the square root of e. So just quick reminder, if I have some number to the m over n, that is equal to the nth root of b to the m, right? So that means that that denominator becomes the index of the root. So if it's a 1/2 power, that means it's a square root. If it's a 1/3 power, it's a third root. So you can actually choose, you could either use the square root, or you can use the exponent. And you'll find, unless you have a button that's expressly for e that doesn't have the exponent, it's actually a lot easier just to use the exponent. So that's how I'm going to plug it in. So we'll go e to, we already have that. I don't need that. E to the 1/2. So it's 1 divided by 2, and we'll close that up, and boom. So we get 1.649, because that last digit rounds up. Okay, now here we have a negative exponent, and remember, negative exponents actually mean dividing, right? So what that means is, oops, let's turn the pen back on. E to the -2 is 1 over e squared, right? Negatives just mean switch the side of the fraction bar you're on. So you could actually plug that in either way, but I think it's probably easier to use the exponent directly, at least on the calculator. So we have e to the, now, if you use the minus here, it's going to think you're trying to subtract something. What you need to use for the negative is this negative. This negative is different than this subtraction. Those are two different operations, even though they look the same. So we got -2, and we'll just close her up. Boom. So that's 0.135. 0.135. Okay, so that's our approximation there. Now the last one, you notice I have an exponent with a square root in it. So same business, right? We want e to the, and now we need a square root. So it's usually, if there's a button that says square, the second function is usually the square root. That is not what I meant to hit. Let's go back. Okay, let's try that again. There, that's what I meant to hit. So square root of 3, and then you need to close both sets of parentheses. A good rule of thumb, count the parentheses that open this way. They should be the same as the number of parentheses you have opening this way, right? So you want to make sure every one of these has one of these matched to it. And then we'll see what we get here. Okay, so we get 5.652. Okay, so that's computing these on the calculator, right? That's really, that's where you're going to do most of your computation. It's very hard to do things with E by hand. Oh God, I'm just thinking about that hurts me. Okay, so now that we have an idea of E and how to take powers of E and things like that, I want to talk real briefly about what it looks like when we graph these things, and then once we get that down, I just want to look at a couple of examples of using it, and then we'll just go from there. Okay, so let's go ahead and clear that off. And I'll go ahead and there's the clear button. All right. So if we're talking about e to the x as a function, It's an exponential function. E is just a number. It's a number raised to a power, just like we did in the previous lecture. The only difference is it happens to be an irrational number this time. It doesn't really change anything. In fact, let's go ahead and broaden this a little bit. Let's put a coefficient out in front. A times e to the let's make it x, since our variable is x over there in the function. Right, a times e to the x. So again, it still has the same shape. What's kind of nice about this, if you make x 0, e to the 0 is still 1, which means that the y-intercept is at a, right? E is positive, and it's not being divided by anything. E is not just positive, but it's bigger than 1. So that means we swoop up to the right. And I still have an asymptote on the x-axis. Now, if you remember from the last time we were talking about exponentials, if the number is smaller than 1, it goes the other direction, right? Well, when we're dealing with e to the x, that's not really what happens, right? We don't usually write 1 over e. What we do instead is we use a negative exponent. And so if it's f of x equals a times e to the negative x, right? So if we make that negative up there, that's what switches which direction it goes. Remember, e to the negative x is the same thing as 1 over e to the x, right? So it is a fraction, right? There's no difference between these two expressions. E to the negative x and 1 over e raised to the x are the same quantity. So it's another way of writing a fraction. You just use a negative exponent instead. And again, you still have oops. Let's try and do that. You still have an asymptote on the x-axis. So all the other stuff, as far as how you graph them, as far as being an exponential function and all that, all of it stays the same, right? It's just a matter of you're dealing with a different base, and then you have to watch out for a negative exponent, which means that you have the other graph, the one that goes down to the right instead of up to the right. All right. So that's just kind of the basics of graphing, just making sure you know that everything we've already learned it still applies. Now, let's see here. I want to look at some examples of this here. Okay, so the first and probably most common example is compound interest. Okay, now compound interest is kind of interesting. That wasn't supposed to be a pun. There's actually two different formulas you use. So we're going to start with the first one. The amount you have is equal to the principal, which is the amount that you started the investment with. You drop that money in the bank, and then it earns interest. And the way it earns the interest is 1 plus r over n raised to the nt. Now we need to know what all of these things are. Well, let's see. P is our principal. R is the interest rate. As a decimal. N is the number of times it's compounded. Now, when something is compounded, like if you have an annual interest rate, and you're going to compound it, let's say quarterly, what that means is that in that period of 1 year, you're going to recompute the interest 4 times, right? So you're going to compute the interest 4 times during the year and then add all that interest up instead of computing it all at the end of the year. And when you break it up into little pieces like that, those are called compounding periods. Okay, so number of times annually compounded. Okay, and then t is time, typically in years, right? Unless your interest rate is you're told it's a monthly interest rate. If you're told your interest rate is monthly, then your time is in months. If you're told your interest rate is annual, then your time is in years. So it depends on what your interest rate is given to you as. Let's see. P is the principal amount of time in R. Yeah, that's all the pieces. Okay. Now, as far as N goes, right? If something is compounded annually, N equals 1. Semi-annually, N equals 2. Quarterly, N equals 4. Monthly, N equals 12. God, you could do daily, N equals 365, right? So if you're told, this is basically all the different things that you could break up N into, how many times you could have things compounded. Then there is continuously compounded. Okay, if something is continuously compounded, that means N is infinity. Now, if you remember the definition of E, it was 1 plus 1 over N to the N as N goes to infinity. Well, you notice that really looks a lot like this thing, doesn't it? Right? This is our E, and it turns out that when the number of times that we're compounding this goes to infinity, it completely changes the formula to A is equal to P times E to the RT, where R is your interest rate and P is still your principal. But it collapsed all that other complicated stuff down and it put it into this real nice equation, the PERT equation, I guess some people call it. I don't know. It reminds me of shampoo. I don't spend a lot of money on shampoo. So, um, anyways, so these are the formulas we're going to be using with compound interest. We have this one right here, and this is for compounded discretely. Discretely means that you can count the number of times it's compounded. And this is for compounded continuously, which is compounded an infinite number of times, right? It's not able to be counted. Okay, so hopefully you have that down, and hopefully you've seen this before, but if you haven't, then let's go ahead and take a look here. So let me go ahead and delete this, and then we'll take a look at an example. Okay, so first example, suppose we have, oh, yeah, this thing works better with the pen on. Okay, suppose you have $12,000 to invest. Okay, I don't know, you got an inheritance or something. Suppose you $12,000. Suppose you have $12,000, and you want to invest it. Boy, I'm having trouble with my spelling here. Okay, so you want to invest at, what do I have here? 6.75% compounded. Let's do compounded quarterly to start out with for 6 years. Okay, now, so let's see here. We have, let's see. It's going to be compounded quarterly, which means that it's it's a finite number of times it's compounded, right? Discrete, that's the word I was looking for. So that means we're using this. right? Okay, see if you can figure out how to plug everything into that, and then we'll take a look and we'll go from there. Okay, so I'm assuming you've paused it and given it an attempt here. So if we want to know the amount after 6 years, it's the principal, P, which is the amount you start with. So it's 12,000 times 1 plus R. Now, R is this 6.75%. So we need to write that 0.0675. You always move the decimal 2 places. Over the number of times it's compounded, and it's quarterly, so that means it's compounded 4 times per year, raised to the NT. So this is 4 times T, right? So N is there, and we just found out actually that T is 6, so we can plug that in too. So the idea is to plug this entire expression into your calculator so that you can get it. And I'm going to do it 2 different ways, just so, because not every calculator shows the whole expression as you're typing it. Okay, so if it does show the whole expression, you can type it in exactly how you see it, right? You have, let's turn it on, 12,000 times 1 plus R, which is 0.0675 divided by N, which is 4. Close that up. Now you want to raise it to the N times T power. So that means if you have some operation going on in the exponent, you need to put parentheses around the exponent. And so that was 4 times 6. And you could do that in your head. You could just type 24 if you wanted. But yeah, so this is what we're looking at. Let's see what we get. Actually, just because, let's do this. I'm going to insert that just because, just so it's clear that it's a multiplication to the calculator. Every once in a while, I know the older TIs, if you forget that, it computes it a little bit differently. Okay, so we have 17930 point. Well, here's an interesting question. Where do we round this off? And the answer would be to the hundredths place, because we're talking about money. So those are your pennies, right? You round it to the nearest penny. And so if you actually made this investment, you would turn $12,000 into almost $18,000. Now, let's see how it changes if we compound monthly. Right? Everything's almost the same. The only difference is we're changing what N is. Okay, so let's see how it changes. So if we compound monthly, it would be 12,000 times 1 plus 0.0675 divided by 12 this time, because it's once a month, raised to the 12 times 6. So we just changed the N's from 4s to 12s. That's all we did. So let's plug it in and see what happens. Yeah, I guess we could do it this way. Instead of typing the whole thing in, I'm going to put the last entry here, and I'm just going to navigate in and change what I see here. So we'll delete, insert 12. Okay, and then, oh yeah, I have to do that. So we'll delete and insert 12. So all we did was change that one number. And if we hit enter, it's still almost $18,000, right? We get 17,971, and this time it's in 22 cents. You notice you make a little bit more when you compound things more often, right? And so that's actually what the goal is when you're investing. You want to get it compounded more often if you can, because you do make a little bit more money. The interest rate actually has a bigger say in that, but nonetheless. Now, I want to look at this one more time, but this time, oops, that is not the selector. There, this is what I wanted. This is what I was trying to do. There we go. I'll delete that. This time, let's make it compounded, oops, continuously. So it's compounded continuously, which means we completely switch equations. It's P times E to the RT. I always loved it when it switched to continuously because the formula is so much easier to type in. You don't have as many places to make mistakes. What that would make it is 12,000 times E to the 0.0675, and T is 6. It's still 6 years. And so that's all we have to plug in this time. So if we're going to plug that in, I get 12,000 times, and I need my e to the x here, and I'm going to type in 0.0675 times 6, and then close my parentheses. And boom. And you notice we made it just a little bit more this time. It's still shy of 18,000, but it's closing in on it. And did that really round to 2 decimal places? That's very interesting. There's probably a whole bunch of zeros in there before it has something else. That's kind of interesting. Anyways, so you can see it is a little bit more than what we were making last time, because the last one where we compounded it monthly, it came to 17,971. So this tacked basically another $20 on top of it. So that's how you deal with interest, right? When you're talking about compound interest, it's those two formulas, either the P times 1 plus R over N to the NT, if it's discrete, if it's compounded discretely, and if it's compounded continuously, it's P times E to the RT, right? Okay, so I want to look at one more example just to show you that this pops up in different places. That is not what I wanted. I wanted this. Yeah, there we go. There. Yeah, so let's look at a second example here. Learning retention, right? And this is an estimate. This is certainly not applicable to every single person, but one of the equations that is used to describe how much you remember is f of x is equal to 80 times e to the negative 0.5 t plus 20. Now, let me describe what we got here. Oh, not t. I used x, so. Okay, x is the number of weeks since learning something, right? So you learned something, x counts the weeks since you learned that. Now, with no, and this is talking about learning with no practice, right? Not trying to refresh yourself or anything else. What the output is, f of x is the percent of knowledge retained after x weeks, right? So this is kind of nice. And again, keep in mind that when you see models like this that are describing things like human behavior, these are an average, right? So on average, people forget at this rate. So we got spring break coming up. And I don't know if you're actually going to be working on stuff over spring break or not, but let's see what happens, how much information you're expected to lose after 1 week with no practice. So what this would be f of 1, which means that it is 80 times e to the negative 0.5 times 1 plus 20. Okay, so let's see what we get. Let's plug this into the calculator. So I have 80 times e to the 0.5, oh, excuse me, negative 0.5. And it's times 1, so that's not going to change anything, right? And then we just need to add 20 to it. So let's see what we get. Boom. So what I get is 68, and I'm going to take this to, well, we'll do this one 3 decimal places. Probably 2 would be more appropriate, but and remember, this is a percent, right? So that means after a week of doing nothing, you're losing more than 30% of your information. You've actually just, as far as your knowledge goes, if you don't do anything, your knowledge can drop from full knowledge to a D's level of knowledge if you don't practice. That's what this model suggests, anyhow. I imagine most of you will be doing at least a little bit over spring break. Okay. Yeah, so really more than anything else, it's a matter of making sure you can plug these things in, right? Oh, and speaking of which, I did forget to put this in here. So I do want to show you the one at a time way to do this. In fact, I'll just use this since we're trying to plug in plugging in things like this. Let's just go ahead and walk through these walk through it one step at a time on the calculator. So if I'm going to calculate something like this, what I really need to be able to do is follow the order of operations. And there's no parentheses here, but we do have an operation up in the exponents. So that needs to go first. So negative 0.5 times 1. So you would do that first. If it was another number, well, then you would multiply that first. Okay, so now we got that. Now we need e to that answer, whatever we get. So we're going to go e to the, and most calculators have a button that says answer. This one, it's actually the second function over the negative sign, not the subtraction, but over the negative sign. What it'll do is it just puts the last answer you got in that spot. So I can say answer, right? So now this is e to this number, right? And then you can hit enter. Okay, and now looking at it, so we just got this part. So we just got this part computed. Now we need to multiply it by 80. So it's times 80. Right, we got that. And then we have to add, what is it, 20. Add 20. Right, and that gets you up to your 68. Right, and you could do this with any number. If I wanted to know, like, I don't know, let's say someone has been missing school for 3 weeks, and I want to have an expectation of what they remember. So I would plug it in here. So we'd have 80 times e to the negative 0.5 times 3 plus 20. So it would be 80 times e to the negative point, oops, that's not a point, 0.5 times 3 plus, oops, that's times, plus 20. Whew, boy, 3 weeks all the way down to 37%. Again, these are numbers that are expected when you don't try to review anything at all. You know, keep that in mind. So that'd be a 0. All right. So I think we have at least a feel for how to plug these things in, for how to do boy, I can't talk today. How to compute them, how to interpret them, at least what we've been given so far. And in any case, the next lecture we're going to be talking about the inverse of an exponential function, which is loads more fun. And I mean that seriously. I actually have a lot of fun with those. But anyways, until next time, keep your pencils and your wits sharp.